Astronomers have found the center of the universe. After decades of searching, countless observations and measurements spanning billions of light years, they finally located it. And the answer is shocking. The center is right here, right where you're sitting, and it's also over there, and everywhere else simultaneously. Every single point in the entire cosmos is the center. This isn't a riddle or a philosophical mind game. This is the actual structure of reality, confirmed by every telescope, every observation, every measurement we've ever made. And it completely breaks our intuition about how the universe should work. Your brain rebels against this idea because every explosion you've ever witnessed has a center point. Drop a stone in a pond, and ripples spread outward from where it hit. Detonate fireworks and sparks radiate from a central burst. Even the grandest explosions we can create, nuclear detonations, have a clear epicenter where the blast originated. So when scientists tell us the universe began with the Big Bang, the ultimate explosion, our minds immediately conjure an image of a central point where it all started, with matter and energy expanding outward into the surrounding void. This mental picture feels so natural, so obviously correct, that most people never question it. But this intuition is completely, fundamentally wrong. For centuries, humanity fought a bitter battle against the idea that we occupy any special or central position in the cosmos. The Copernican revolution shattered our geocentric worldview, proving that Earth wasn't the center of the universe, but merely one planet orbiting an ordinary star. Then we discovered our sun was just one of hundreds of billions in the Milky Way galaxy, located not at the galactic center but in a boring spiral arm about 2/3 of the way out. As telescopes improved, we realized our galaxy itself was nothing special, just one of trillions spread throughout an incomprehensibly vast universe. Each discovery pushed humanity further from center stage, teaching us cosmic humility. We are not special, we are not central. We are unremarkable inhabitants of an unremarkable planet, orbiting an unremarkable star in an unremarkable galaxy, in an unremarkable region of space. But now, cosmology presents us with something that sounds like it contradicts everything we've learned. When we measure the universe's expansion, we find that galaxies in every direction are moving away from us. The Milky Way appears to sit at the exact center of a cosmic explosion, with everything else fleeing outward. This seems to place us right back at the center, violating 500 years of scientific progress. How can this be? Are we special after all? Did the universe explode from precisely our location? The answer is far stranger than you imagine, and understanding it requires completely rewiring how you think about space itself. Imagine a balloon with dots drawn on its surface. As you inflate the balloon, each dot moves away from every other dot. But here's the critical insight. There is no center on the balloon's surface. The center of the balloon exists in three-dimensional space, in a dimension the surface dwellers cannot access. If you were a two-dimensional creature living on that balloon surface, you would see all other dots moving away from you, and you might naturally conclude you were at the center. But so would every other dot. Each observer sees the same pattern, every point moving away from every other point. The expansion has no center on the surface itself because the surface is all that exists for the inhabitants. The center, if it has any meaning at all, lies in a dimension beyond their reality. This is exactly how our universe works, except instead of a two-dimensional surface expanding in three-dimensional space, we have three-dimensional space expanding in ways our minds struggle to visualize. The center isn't somewhere we can point to or travel to. It isn't in our past or our future. The concept of center simply doesn't apply to cosmic expansion in the way our intuition demands. In 1929, Edwin Hubble made the observation that would revolutionize our understanding of the cosmos. Using the most powerful telescope of his era at Mount Wilson Observatory, he measured the distances and velocities of galaxies beyond our own. What he discovered should have been impossible according to the static universe model that dominated scientific thinking at the time. Every galaxy he observed was moving away from us. Not just a few galaxies, not just galaxies in one direction, but every single galaxy in every direction showed light shifted toward the red end of the spectrum, indicating recession. Even more bizarre, galaxies farther away were receding faster than nearby ones. A galaxy 10 million light-years away might be moving away at 500 kilometers per second. A galaxy 20 million light-years away was receding at 1,000 kilometers per second. The relationship was perfectly proportional, now known as Hubble's law. At first, this seemed to place Earth at the center of a cosmic explosion. Imagine standing in the middle of a field while everyone else runs away from you. The natural conclusion would be that you're standing at the exact spot where something dramatic happened, the epicenter. Hubble's observations appeared to show exactly this pattern. We seemed to occupy the unique position from which the universe had exploded, with all matter fleeing outward from our location. This was the natural interpretation, the obvious explanation that fit our intuitive understanding of explosions and expanding things. But this interpretation created a massive problem. It violated the Copernican principle, the hard-won understanding that we don't occupy a special place in the cosmos. What were the odds that, of all the galaxies in the universe, the spot that would eventually become the Milky Way just happened to be the exact center point of cosmic expansion? It seemed absurdly unlikely, almost as improbable as the pre-Copernican belief that Earth sat motionless at the universe's center while everything else revolved around us. Either we had stumbled into an extraordinary cosmic coincidence, or something much stranger was happening. The critical insight came from understanding that galaxies aren't moving through space in the conventional sense. Space itself is expanding between them. This distinction seems subtle, but it changes everything. Picture it this way. Imagine you and a friend are standing on opposite sides of a giant rubber sheet, each holding a penny. If your friend walks toward the edge of the sheet while you stand still, the penny moves through the rubber. But if instead the entire sheet is stretched uniformly in all directions, both pennies move apart without either one traveling across the rubber surface. The rubber itself is expanding, carrying the pennies along with it. This is what's happening with galaxies and cosmic expansion. Galaxies aren't rocketing through space like debris from an explosion. The fabric of space itself is stretching, and galaxies are embedded in that fabric like raisins in rising bread dough. As the dough rises, raisins move apart not because they're traveling through the dough, but because the dough between them is expanding. Each raisin sees all other raisins moving away, with distant raisins receding faster than nearby ones, exactly matching Hubble's observations. And here's the crucial point. There is no center to the expansion. Every raisin has an equal claim to being the center, because the expansion looks identical from every raisin's perspective. Think about an infinite sheet of graph paper, where each square is 1 centimeter on each side. Now, imagine that cosmic expansion causes every square to simultaneously double in size. Suddenly, each square is 2 centimeters on each side. Pick any intersection point on the graph paper and you'll notice that every other intersection has moved away from it. Points that were 1 square away are now 2 squares away. Points that were 10 squares away are now 20 squares away. The farther away a point was, the more distance has opened up between you and it. This perfectly replicates Hubble's observations. But is there a center to this expansion? No. Every single intersection point sees the exact same pattern. Every point can legitimately claim to be the center because expansion looks identical from everywhere. The critical difference between motion through space and expansion of space resolves our paradox. When something moves through space, there's a clear reference frame. A rocket launching from Earth moves through space relative to Earth. But cosmic expansion has no such reference frame. Space itself is growing, carrying everything embedded in it. This creates the appearance that we're at the center, but it's an illusion created by the nature of uniform expansion. Every observer, anywhere in the universe, sees exactly the same pattern. You might immediately ask, if space itself is expanding, what is it expanding into? This question seems perfectly reasonable and natural. After all, everything we've ever seen expand does so by growing into surrounding space. A balloon expands into the air around it. A city expands into the surrounding countryside. Even an explosion expands into the space it's detonating within. So surely the universe, if it's expanding, must be growing into something, some pre-existing void or arena that contains it. But this question, as natural as it feels, is based on a flawed assumption about the nature of space itself. We'll return to this question later, but the short answer is this: the universe isn't expanding into anything because there is no outside for it to expand into. Space is all that exists, and asking what it expands into is like asking what's north of the North Pole. The question itself is malformed. What matters for now is understanding the revolutionary implication of expanding space. From every galaxy's perspective, it appears to be at the center with everything else receding. An alien astronomer in the Andromeda galaxy, 2.5 million light-years away, would look out at the cosmos and see exactly what we see. All galaxies moving away in every direction, with more distant galaxies receding faster. They would measure the same expansion rate we measure. They would detect the same uniform cosmic microwave background radiation we detect. They would conclude, just as we did, that their galaxy appears to sit at the center of expansion, and they would be just as right and just as wrong as we are. This observation reveals something profound about the structure of space itself. The universe obeys what cosmologists call the cosmological principle. It looks roughly the same from every vantage point. This principle has two components. Homogeneity means the universe has the same average properties everywhere. Isotropy means it looks the same in every direction. Together, these properties describe a universe with no special locations and no preferred directions. Every point is equivalent to every other point. Every direction is equivalent to every other direction. The strongest evidence for the cosmological principle comes from the cosmic microwave background, the afterglow of the Big Bang itself. This radiation fills all of space, and its temperature has been measured with extraordinary precision. What astronomers found was shocking uniformity. In every direction we look, the cosmic microwave background has a temperature of 2.7 Kelvin, with variations of only 1 part in 100,000. These tiny variations, while incredibly important for understanding structure formation, are dwarfed by the overwhelming uniformity. No matter which direction you point your telescope, you see essentially the same temperature, the same properties, the same features. Galaxy surveys reveal the same pattern. Astronomers have mapped millions of galaxies across vast regions of space, looking for patterns in their distribution. On the largest scales, the universe appears remarkably uniform. There's no preferred axis along which galaxies align. There's no center toward which galaxies cluster more densely. There's no edge where galaxies suddenly stop. The large-scale structure looks the same whether you survey the northern sky or the southern sky, whether you look toward the galactic center or away from it. This isn't to say the universe is perfectly smooth. Galaxies cluster into groups, groups cluster into clusters, and clusters form even larger structures called superclusters. But average over large enough volumes, say several hundred million light-years, and the density becomes remarkably consistent. Imagine you could teleport instantaneously to a galaxy 10 billion light-years away in any direction. What would you see? You'd see exactly what we see from here. Galaxies in every direction moving away from you. The cosmic microwave background glowing uniformly in all directions. The same physical laws operating, the same types of galaxies and stars, the same expansion rate. There would be no way to determine that you'd moved at all, except that you'd be looking at different specific galaxies. The cosmic scenery would have changed, but the cosmic environment would be identical. This leads to an unsettling but inescapable conclusion. If every point in the universe sees the same expansion pattern, if there's no observation that could tell us we're in a special location, then either every point is the center, or the concept of center is meaningless when applied to the universe. Both of these statements are essentially saying the same thing in different ways. The center of the universe is everywhere because the universe has no center. But how do we know the expansion is really uniform? How can we be certain we're not just in a special region that happens to look symmetric? The answer comes from multiple independent observations that all point to the same conclusion. Type 1. A supernovae provide some of the strongest evidence. These stellar explosions occur when white dwarf stars accumulate too much matter and undergo catastrophic nuclear detonation. The physics of these explosions is remarkably consistent, causing every Type 1 supernova to reach approximately the same peak brightness. This makes them perfect standard candles for measuring cosmic distances. When you observe a Type 1 supernova, you can determine its distance by comparing its apparent brightness to its known intrinsic brightness. The inverse square law tells us that brightness decreases with the square of distance. An object twice as far away appears 4 times dimmer. An object 10 times farther away appears 100 times dimmer. By measuring how bright a supernova appears and knowing how bright it actually is, you can calculate exactly how far away it must be to appear that dim. But supernovae also provide velocity information through redshift measurements. Light from distant galaxies is stretched to longer, redder wavelengths by cosmic expansion. The amount of stretching tells us how much the universe has expanded since the light was emitted, which in turn tells us the galaxy's recession velocity. By combining distance measurements from supernovae with redshift measurements from the same objects, astronomers can map the expansion history of the universe. In 1998, 2 independent teams studying distant supernovae made a discovery that would earn them the Nobel Prize. The supernovae they observed were fainter than expected. This meant they were farther away than standard expansion models predicted. The universe hadn't been expanding at a steady rate or slowing down as expected. It was accelerating. Some mysterious force, now called dark energy, was pushing space apart faster and faster. This discovery revolutionized cosmology, but for our purposes, what matters is the symmetry of the observations. No matter which direction astronomers look, they find the same relationship between distance and redshift. Galaxies 5 billion light-years away show redshift values consistent with that distance. Galaxies 10 billion light-years away show proportionally higher redshifts. This relationship holds in every direction sampled. There's no direction where distant galaxies are blue-shifted, indicating they're moving toward us. There's no direction where the redshift-distance relationship is significantly different. The pattern is identical across the entire sky, confirming that expansion is indeed uniform, and that we're not in a special location. The observable universe is not the universe. This distinction is absolutely critical, and most people miss it entirely. When astronomers talk about the observable universe, they're describing a sphere centered on Earth with a radius of about 46 billion light-years. That's the region from which light has had time to reach us since the Big Bang. But this sphere is not a boundary of space itself. It's a boundary of observation, a horizon beyond which we simply cannot see. The actual universe extends far beyond this horizon, possibly infinitely far, filled with galaxies and stars and planets we will never observe, never detect, never know about. The cosmic horizon currently sits at roughly 46 billion light-years from Earth in every direction. You might immediately notice something strange about this number. If the universe is 13.8 billion years old, and light travels at a finite speed, shouldn't the farthest we can see be 13.8 billion light-years? This is where cosmic expansion creates a counterintuitive result. A galaxy that emitted light 13.8 billion years ago, when the universe was very young, has not remained in the same location. While its light traveled toward us, space itself was expanding, carrying that galaxy farther and farther away. By the time the light reaches our telescopes, that galaxy has been carried by expansion to a distance of about 46 billion light-years. We're seeing where it was, not where it is now. This horizon appears to be centered perfectly on us. No matter which direction we look, the edge of the observable universe sits at the same distance, creating a perfect sphere with Earth at its center. This seems to contradict everything we just established about having no special location. Are we at the center after all? Have we been led astray? The answer is no, and understanding why reveals something profound about the nature of cosmic horizons. Every observer in the universe has their own horizon, centered on them. An alien astronomer in a galaxy 10 billion light-years away has their own 46 billion light-year horizon centered on their location. Their observable universe overlaps with ours, but is not identical to it. They can see regions of space we cannot, and we can see regions they cannot. Horizons are observer-dependent features, not universal boundaries. It's like standing in thick fog on a flat plain. You can see 100 meters in every direction before the fog obscures your view. This creates a circle of visibility centered on you. But the fog doesn't actually have a boundary. If you walk forward, your circle of visibility moves with you. Someone standing a kilometer away has their own circle, overlapping with yours but centered on them. Neither of you occupies a special location. The limitation is perceptual, not spatial. But why do cosmic horizons exist at all? The answer lies in two fundamental facts about our universe. Light travels at a finite speed, approximately 300,000 kilometers per second, and the universe has a finite age of 13.8 billion years. These two facts combine to create an absolute limit on how far we can see. Light from the most distant objects has been traveling toward us since the earliest moments of cosmic history. Light that left even earlier hasn't reached us yet. Light from objects beyond a certain distance hasn't had time to reach us and never will due to accelerating expansion. The naive calculation suggests that if the universe is 13.8 billion years old, we should be able to see objects up to 13.8 billion light years away. Light has had that much time to reach us, so anything farther simply hasn't sent us its light yet. But this calculation ignores cosmic expansion. During the 13.8 billion years that light has been traveling toward us, space itself has been stretching. The galaxy that emitted the light has been carried farther away by this expansion. To understand the true distance to the cosmic horizon, we need to account for how much space has expanded during the light's journey. Here's what actually happened. Shortly after the Big Bang, a galaxy emitted light in our direction. That moment, the galaxy was relatively close to our location, perhaps only 40 million light-years away in terms of the space that existed at that time. The light began its journey toward us, traveling through expanding space. As it traveled, the space it moved through was continuously stretching, which had two effects. First, it stretched the wavelength of the light itself, causing cosmological redshift. Second, it increased the distance between the galaxy and our location. After traveling for 13.8 billion years, the light finally reaches us. But the galaxy that emitted it is no longer 40 million light-years away. Space has expanded so much during that time that the galaxy is now approximately 46 billion light-years distant. We see the galaxy as it was 13.8 billion years ago, but it exists today at a much greater distance than the light has actually traveled. This expansion-adjusted horizon defines our observable universe. But there's another horizon that's even more limiting. The cosmic event horizon marks the boundary beyond which light will never reach us, no matter how long we wait. This horizon exists because cosmic expansion is accelerating. Galaxies beyond a certain distance are receding from us faster than light can travel toward us through the expanding space between us. These galaxies are not moving through space faster than light, which would violate relativity. Rather, space itself is expanding fast enough that the distance between us and them grows faster than light can traverse it. No light emitted by these galaxies today will ever reach us. They are permanently beyond our observational reach. Currently, the cosmic event horizon sits at about 16 billion light-years from Earth. Any galaxy farther than this critical distance is forever inaccessible to us. Light leaving those galaxies right now, traveling at maximum speed through space, will make some progress toward us initially. But as cosmic expansion accelerates, driven by dark energy, the space between us expands faster and faster. Eventually, despite the light's motion toward us, the distance between the light and Earth begins increasing. The light makes progress through space but falls farther and farther behind as space stretches. It's like trying to walk forward on a treadmill that's accelerating faster than you can run. Eventually, no matter how fast you walk, you're moving backward relative to the room. This raises an immediate and unsettling question. What exists beyond our cosmic horizon? What fills the space we cannot see and will never see? The honest scientific answer is we don't know with absolute certainty. We cannot observe it, cannot measure it, cannot gather data about it. Any claims about regions beyond our observational limits are necessarily speculative. However, we can make educated guesses based on what we do see. The scientific consensus is that space beyond our horizon probably contains more of the same. More galaxies, more stars, more planets, all following the same physical laws we observe in our region. This conclusion rests on the cosmological principle. If the universe is homogeneous and isotropic, if it has the same properties everywhere, then the region beyond our horizon should resemble the region within it. We see no evidence of any boundary or edge to cosmic structure. Galaxy surveys show the same average density in every direction we look, out to the farthest distances we can observe. There's no indication that we're near an edge, or that conditions change dramatically at the limits of our vision. The simplest explanation is that what we see is representative of the whole. But how much more space exists beyond what we can see? This is where the numbers become almost incomprehensibly large. The inflationary universe model suggests that in the first fraction of a second after the Big Bang, space underwent a period of exponential expansion, growing faster than light by enormous factors. During this inflationary epoch, which lasted only about 10 to the negative 32 seconds, a region smaller than an atom expanded to a size vastly larger than our current observable universe. The observable universe we see today is just one tiny patch of this inflated region. Conservative estimates based on inflationary models suggest the full universe is at least 10 to the 23rd times larger than our observable patch. That's 1 followed by 23 zeros. Our observable universe contains about 2 trillion galaxies. If the full universe is 10 to the 23rd times larger, it contains approximately 2 trillion times 10 to the 23rd galaxies. That's a number so large it defies comprehension. But even this might be a vast underestimate. Many models of inflation predict that the full universe is actually infinite in extent, stretching forever in all directions, containing infinite galaxies, infinite stars, infinite everything. The cosmic horizon hasn't always been 46 billion light-years away. It has grown over time as light from more distant regions has reached us. At the moment of the Big Bang, the horizon was 0. No light had traveled anywhere yet, so nothing was visible. 1 second after the Big Bang, the horizon had grown to encompass the light that could travel 1 light second. 1 year later, it encompassed 1 light-year. The horizon has been steadily expanding throughout cosmic history as we receive light from progressively more distant sources. Roughly speaking, the horizon grows by about 1 light-year per year. Each year, light from objects 1 additional light-year away reaches us for the first time. This means we're constantly seeing cosmic objects that have existed for billions of years, but are only now coming into view. Imagine a galaxy 10 billion light-years away. That galaxy has been shining for most of cosmic history, but its light is only now reaching Earth. From our perspective, this galaxy just appeared, but from the galaxy's perspective, it has been there all along. Our expanding horizon continuously reveals portions of the universe that have existed all along, but were previously beyond our observational reach. However, while our particle horizon, the boundary of what we have seen, grows larger, our event horizon, the boundary of what we will ever see, is actually shrinking due to cosmic acceleration. Dark energy is causing expansion to accelerate, pushing distant galaxies away from us faster and faster. Galaxies that are currently visible will eventually cross our event horizon and disappear from view. Their light will continue reaching us for a while, but it will become increasingly redshifted, stretched to longer and longer wavelengths, growing dimmer and dimmer. Eventually, the light will be stretched beyond detection, and these galaxies will fade into observational oblivion. The timeline for this cosmic disappearance is staggering. In roughly 150 billion years, assuming dark energy remains constant, only our local group of galaxies will remain visible. The Milky Way, Andromeda, Triangulum, and their satellite galaxies will have merged into one giant elliptical galaxy. But beyond this merged system, the sky will be empty. Every other galaxy will have been carried beyond our event horizon by accelerating expansion. Future astronomers living in this distant era will look out at the cosmos and see almost nothing. They will observe a single giant galaxy surrounded by vast, empty darkness. They will have no evidence that billions of other galaxies once filled space. They will have no access to the cosmic microwave background, which will have been redshifted into undetectability. They may conclude they live in a small, static, eternal universe, with no knowledge of the Big Bang, cosmic expansion, or the rich cosmic history that actually occurred. This future scenario reveals something disturbing about our current cosmic knowledge. We live in a special epoch, not a special location. We happen to exist at a time when the cosmic microwave background is still detectable, when billions of galaxies are still visible, when we can study cosmic expansion and structure formation. In the far future, this window will close. In the distant past, before stars formed and galaxies assembled, there was nothing to observe. We exist during a relatively brief period of cosmic history when the universe reveals itself. This temporal specialness is different from spatial specialness, but it's still a form of cosmic privilege we shouldn't take for granted. Horizons also connect to one of the deepest mysteries in cosmology: causality. The causal horizon defines regions of space that can or cannot have exchanged information. If two regions are separated by more than light could have traveled between them, they cannot have influenced each other. They exist in causally disconnected regions of space-time. This creates what cosmologists call the horizon problem. When we observe the cosmic microwave background, we see radiation coming from opposite sides of the sky, from regions separated by about 92 billion light-years today. These regions have never been in causal contact. Light from one region has never had time to reach the other, yet both regions have almost exactly the same temperature, the same properties, the same characteristics. How did they reach such precise agreement without ever communicating? The traditional Big Bang model offers no explanation. If these regions were never in causal contact, there's no physical mechanism to synchronize their temperatures. They should show random variations, dramatically different properties. The observed uniformity seems to require some form of coordination that standard cosmology cannot provide. This was one of the most troubling problems in cosmology for decades. Cosmic inflation solves this problem elegantly. Before inflation, when the universe was a tiny fraction of a second old, all the regions we can see today were compressed into an incredibly small volume. This volume was so small that different parts of it were in causal contact. They could exchange energy and information. They had time to reach thermal equilibrium, settling into the same temperature. Then inflation occurred. This tiny region underwent exponential expansion, growing by at least 26 orders of magnitude in less than 10 to the negative 32 seconds. The causally connected region that had reached equilibrium was stretched to encompass what would become our entire observable universe and far beyond. The uniformity we see in the cosmic microwave background isn't mysterious coordination between disconnected regions. It's the remnant of thermal equilibrium that was established before inflation separated these regions. Our observable universe, all 46 billion light-years of it in every direction, was once compressed into a region smaller than an atom. Every part of this region could communicate with every other part. Quantum fluctuations during this period created tiny variations in density and temperature. Inflation stretched these quantum fluctuations to cosmic scales, creating the temperature variations we see in the cosmic microwave background. These variations, only one part in 100,000, eventually grew through gravitational attraction into all the structure we see today. Every galaxy, every star, every planet descended from quantum uncertainty in a region smaller than a subatomic particle. The cosmic horizon is not a feature of the universe itself. It's a feature of observation, a limitation imposed by the finite speed of light and the finite age of the universe. Consider ships sailing on the ocean. Each ship has a horizon, a circle beyond which they cannot see due to the Earth's curvature. A ship 100 kilometers away from you has its own horizon, centered on it. Your horizon and their horizon are different circles, overlapping, but not identical. The horizon is observer-dependent. It moves with the observer. There is no universal ocean horizon that all ships share. The same principle applies cosmically. An alien astronomer in the Andromeda Galaxy, 2.5 million light-years from Earth, has their own cosmic horizon. It's centered on Andromeda and extends 46 billion light-years in every direction from that galaxy. This horizon overlaps substantially with ours. Most of what they can see, we can also see, and vice versa. But the boundaries don't match perfectly. There are regions of space visible to them that lie beyond our horizon. There are regions visible to us that lie beyond theirs. For an observer in a galaxy 10 billion light-years away, the difference becomes more pronounced. Their observable universe is a sphere centered on their location. Our observable universe is a sphere centered on our location. These spheres overlap, but roughly half of what they can see is invisible to us, and half of what we can see is invisible to them. Neither observer has access to the full picture. Each sees their own limited patch of a vastly larger whole. This leads to a profound philosophical implication. Reality extends far beyond what any observer can access. The universe is fundamentally larger than any possible observation of it. No matter how advanced our technology becomes, no matter how long we wait, we can never see beyond our cosmic horizon. There are galaxies, stars, planets, possibly even other civilizations that exist in regions of space causally disconnected from us. Their light will never reach us. Our light will never reach them. We exist in parallel but forever separate observable universes, all embedded in the same larger cosmos. The universe doesn't care about observation. It extends infinitely or near infinitely in all directions, indifferent to the limited perspective of any observer. We are not at the center because there is no center. We simply occupy one location among infinite locations, each with its own horizon, each with its own observable universe. Einstein's general relativity revealed something profound about the fabric of reality. Space itself can be curved. Not curved through some higher dimension that we can visualize, but curved in its own intrinsic geometry. This curvature isn't just an abstract mathematical concept. It has observable consequences that determine the ultimate fate of the entire universe. The geometry of space dictates how cosmic expansion behaves, whether the universe is finite or infinite, and what will happen in the distant future. Everything depends on the shape of space itself. There are three possible geometries for the universe, three fundamental ways that space can be shaped. The first is positive curvature, where space curves back on itself like the surface of a sphere. The second is negative curvature, where space curves away from itself like a saddle. The third is flat space, the Euclidean geometry we learn in school extended to cosmic scales. Each geometry has dramatically different properties and implies a completely different cosmic destiny. The simplest way to understand these geometries is through the triangle test. Draw a triangle in space and measure the sum of its three interior angles. In flat Euclidean space, the angles always sum to exactly 180 degrees, just as you learned in geometry class. But in curved space, this fundamental rule breaks down. In positively curved space, triangle angles sum to more than 180 degrees. Draw a triangle on the surface of a sphere, and you'll see this directly. Start at the North Pole, draw a line down to the equator, travel along the equator for a quarter of the way around, then draw a line back up to the North Pole. You've created a triangle with three 90-degree angles, summing to 270 degrees, far more than the 180 you would get on a flat surface. In negatively curved space, triangle angles sum to less than 180 degrees. The more extreme the curvature, the more the sum deviates from 180. Another way to detect curvature is through parallel lines. In flat space, if you start with two parallel lines, they remain parallel forever, never converging or diverging, always maintaining the same distance apart. But curvature changes this. In positively curved space, initially parallel lines eventually converge and meet. Think of longitude lines on Earth. They're parallel at the equator but converge and meet at the poles. In negatively curved space, initially parallel lines diverge, growing farther and farther apart as they extend. These geometric properties have cosmic consequences. If space has positive curvature, the universe is finite. If space is flat or negatively curved, it's almost certainly infinite. A positively curved universe has a geometry like the two-dimensional surface of a three-dimensional sphere, but extended to three-dimensional space existing as the surface of a four-dimensional hypersphere. This is impossible to visualize directly because we can't perceive four spatial dimensions, but the mathematics is precise. In such a universe, space curves back on itself. If you traveled in what seemed like a perfectly straight line, heading in one direction and never turning, you would eventually return to your starting point, just as a ship sailing straight across the ocean eventually returns to where it began by circling the globe. The universe would be finite but unbounded, having no edge but also not extending infinitely. The key feature of a closed, positively curved universe is that it contains a finite volume of space. You could, in principle, count every galaxy in such a universe. There would be a largest distance possible, a cosmic circumference. If the universe were small enough, light could complete a full circuit around it, creating bizarre observational consequences. You might see the same galaxy in multiple directions, viewing it from different angles at different times in its history. Astronomers have searched for such repeating patterns in the cosmic microwave background and in galaxy surveys. If we saw the same arrangement of temperature fluctuations or galaxy clusters repeated in different parts of the sky, It would indicate we're seeing the same region from multiple directions, proving space curves back on itself. The ultimate fate of a closed universe depends on its total energy content. If the universe contains enough matter and energy, gravity will eventually overcome expansion. The universe will reach a maximum size, stop expanding, and begin contracting. Space will shrink. Galaxies will be pulled back together, and eventually everything will collapse into what cosmologists call the Big Crunch, a cosmic doomsday where the universe ends in a singular point of infinite density, the opposite of the Big Bang. However, observations strongly disfavor a closed universe. We've looked for repeating patterns and found none. We've measured the geometry and found it to be flat, not positively curved. While we can't completely rule out a closed universe if it's enormous, much larger than our observable region, current evidence suggests this is not the geometry of our cosmos. A negatively curved universe has hyperbolic geometry, resembling the shape of a saddle extended to 3 dimensions. Imagine a surface that curves downward in one direction and upward in another, like a Pringles chip. This geometry has profoundly strange properties. Space curves away from itself, creating more room than you'd expect. If you drew a circle in negatively curved space and measured its circumference, you'd find it's larger than 2 pi times the radius, the formula that works in flat space. The farther you go from a central point, the more excess space you encounter. Volume grows faster than it would in flat geometry. A negatively curved universe is infinite in extent. There's no way to travel in a straight line and return to your starting point. The universe extends forever in all directions, containing infinite space, infinite galaxies, infinite everything. The ultimate fate of an open, negatively curved universe is eternal expansion. Expansion never stops, never reverses. The universe grows forever, becoming colder and emptier with each passing eon. Eventually, it approaches heat death, a state of maximum entropy where all usable energy has been expended and nothing interesting can ever happen again. However, distinguishing between a flat universe and a slightly negatively curved one requires extraordinarily precise measurements. Both geometries lead to infinite space and eternal expansion. The difference lies in subtle details of how expansion evolves over time. A flat universe has Euclidean geometry, the geometry we intuitively understand from everyday experience. Triangles have angles summing to 180 degrees. Parallel lines remain parallel forever. The Pythagorean theorem works exactly as taught in school. This is the geometry that feels natural because it's what we experience locally. Earth's surface appears flat when you're standing on it, even though it's actually spherical. Similarly, cosmic space appears flat locally even if it has slight curvature. But measurements indicate that the universe isn't just locally flat. It appears to be flat on the largest scales we can measure, extending far beyond our observable region. A flat universe sits at the critical boundary between open and closed, between positive and negative curvature. This critical geometry requires a precise energy density called the critical density. If the universe has exactly this density, not slightly more, not slightly less, but exactly the critical value, then space is flat. The critical density depends on the expansion rate. Currently, it equals about 5 atoms of hydrogen per cubic meter of space. This seems like almost nothing, and it is. Space is extraordinarily empty. But this tiny density is enough to make the difference between a universe that expands forever and one that eventually collapses. The remarkable thing is that our universe's actual density appears to match the critical density almost exactly. When we add up all the matter and energy in the universe, ordinary matter, dark energy, everything, the total equals the critical density within measurement uncertainty. This is the coincidence problem. Why should the universe's density be so precisely tuned to this critical value? There's no obvious reason. If the density were slightly higher, we'd have a closed universe that would already be recollapsing. If it were slightly lower, we'd have an open universe with obvious negative curvature. Instead, we find ourselves precisely balanced at the critical density, giving us flat geometry. This seems like an extraordinary coincidence requiring explanation. The ultimate fate of a flat universe depends on what fills it. In a matter-dominated flat universe, expansion would continue forever but gradually slow, approaching a constant rate. But we don't live in a matter-dominated universe. We live in a dark, energy-dominated universe. Dark energy makes up about 68% of the universe's total energy content, and unlike matter, dark energy doesn't dilute as space expands. This causes expansion to accelerate rather than slow. The future of our flat universe is eternal accelerating expansion, with space stretching faster and faster, galaxies receding from each other at ever-increasing rates, until eventually almost nothing remains visible from any given location. Flatness was unexpected. Cosmologists had no strong theoretical reason to believe the universe would be precisely flat. Before we could measure the geometry, either outcome seemed plausible. We might have a closed universe, an open universe, or a flat one. Finding the universe to be flat was surprising because flatness represents an unstable equilibrium. Any deviation from perfect flatness in the early universe would have grown rapidly over time. If the early universe were slightly closed, it would have quickly become more closed, leading to obvious positive curvature today. If it were slightly open, it would have quickly become more open, leading to obvious negative curvature today. For the universe to be flat today, it must have been extraordinarily flat in the beginning, fine-tuned to incredible precision. This fine-tuning demanded an explanation. How do we actually measure the geometry of the universe? The primary method involves analyzing patterns in the cosmic microwave background radiation. Remember, this is light from 380,000 years after the Big Bang, when the universe first became transparent. At that time, the universe was filled with sound waves, pressure fluctuations traveling through the hot plasma. These sound waves had a characteristic scale determined by how far sound could travel in the time available. This scale left an imprint in the cosmic microwave background as regions of slightly higher and lower temperature. When we observe the cosmic microwave background today, we see this pattern of hot and cold spots across the sky. The angular size of these spots depends on the universe's geometry. Think of it this way. The physical size of the hot spots was set by sound wave physics in the early universe. But how large they appear on the sky depends on how light has traveled from them to us, and that journey depends on the curvature of space. In a positively curved universe, light paths converge, making distant objects appear larger than they would in flat space. The hot spots would look bigger. In a negatively curved universe, light paths diverge, making distant objects appear smaller. The hot spots would look smaller. In flat space, light travels in straight lines, and the spots appear at a specific predicted angular size. Multiple satellites have measured the cosmic microwave background with extraordinary precision. The Wilkinson Microwave Anisotropy Probe, WMAP, mapped the entire sky in microwave frequencies, measuring temperature variations to a few millionths of a degree. The Planck satellite, launched later, achieved even better precision. Both missions measured the angular size of the cosmic microwave background hotspots and found them to be exactly the size predicted for flat geometry. The universe is flat to within about 0.4% measurement uncertainty. This is an astonishing level of precision, and it tells us unambiguously that we do not live in a significantly curved universe. What does it mean for space to be flat on cosmic scales? If you could construct a triangle with sides 10 billion light-years long, stretching across vast expanses of space connecting distant galaxy superclusters, and you could somehow measure the interior angles, you would find they sum to 180 degrees plus or minus a tiny fraction of a degree, well within measurement error. Space obeys Euclidean geometry to extraordinary precision across the entire observable universe. This flatness extends as far as we can see, suggesting it continues far beyond our observational horizon. The scientific consensus is clear. All measurements indicate the universe is spatially flat. And if space is flat, extending in all directions with no curvature to close it back on itself, it is almost certainly infinite in extent. Flat geometry, combined with the cosmological principle, which tells us the universe has the same properties everywhere, implies that space goes on forever. There is no edge, no boundary, no place where space stops. Galaxies extend infinitely in all directions, following the same statistical properties we observe in our local region. The universe contains infinite space, infinite matter, infinite galaxies, infinite stars, infinite planets. This immediately raises an objection. How can space be infinite if the Big Bang was a singularity, a single point? If everything came from a point, how can there now be infinite space? The resolution to this paradox requires understanding that infinity can exist at every moment. An infinite universe was infinitely large at the Big Bang. It was infinitely large 1 second after the Big Bang. It is infinitely large today. What changed is not the infinity, but the density and the scale factor. At the Big Bang, infinite space existed, but every region was infinitely dense and infinitely hot. As expansion occurred, that infinite space stretched. Densities decreased, temperatures dropped, but the space remained infinite. The Big Bang didn't happen at a point. It happened everywhere simultaneously throughout infinite space. If space is truly infinite, our observable universe is literally 0% of the total, an infinitesimal fraction. A sphere with a 46 billion light-year radius is nothing compared to infinity. No matter how large a finite number, it's 0% of infinity. This means that everything we can see, every galaxy in every direction out to the cosmic horizon, represents an utterly negligible sample of what exists. The vast majority of the universe, infinite in extent, lies forever beyond our observation. We will never see it, never detect it, never know anything about it except through inference and theory. The flatness of the universe presented a major theoretical problem for decades. Why is space so precisely flat? This is called the flatness problem. The issue is that flatness represents an unstable equilibrium point. Imagine balancing a pencil on its tip. If the pencil is exactly vertical, it will remain balanced. But any tiny deviation, even microscopic, will cause it to fall. The slightest push and it topples over. Flatness works the same way cosmologically. For the universe to be flat today, it must have been flat to incredible precision in the early universe. Any small deviation from flatness would have grown exponentially over time. Let's quantify this. 1 second after the Big Bang, for the universe to end up as flat as we observe it today, the density had to match the critical density to better than 1 part in 10 to the 15th. That's precision to 15 decimal places. At even earlier times, the required fine-tuning is more extreme. Why would the early universe have had exactly the right density to produce flatness? There's no mechanism in standard Big Bang cosmology to set this initial condition. It seems like an arbitrary coincidence that demands explanation. Cosmic inflation provides that explanation. Inflation is a period of exponential expansion that occurred in the first tiny fraction of a second after the Big Bang, lasting only about 10 to the negative 32 seconds. During inflation, space expanded by at least 26 orders of magnitude, possibly much more. A region smaller than an atom grew to larger than the currently observable universe. This explosive expansion had many consequences, but one of the most important is that it stretched space flat. Imagine inflating a balloon. Start with a small balloon, wrinkled and irregular. As you blow it up, the surface becomes smoother. Inflate it to the size of a room, and any small patch of the surface appears quite flat. Inflate it to the size of Earth, and you'd need sensitive instruments to detect any curvature at all. Inflate it to the size of the observable universe, and any measurable patch would appear perfectly flat to any conceivable measurement precision. This is what inflation did to the universe. Whatever curvature existed before inflation, the exponential expansion stretched it smooth, making space appear flat to far better precision than we can measure. Inflation makes a specific prediction. The universe should be flat to within the limits of measurement. Not approximately flat, not mostly flat, completely flat as far as we can tell. This is exactly what we observe. The Planck satellite measured curvature at the 0.4% level and found none. Future missions with even better sensitivity will push this limit further, but inflation predicts they will continue to find flatness. The universe's geometry matches inflation's prediction perfectly, providing strong evidence that inflation actually occurred. Space is flat because inflation stretched it flat, and that flatness has persisted throughout the subsequent 13.8 billion years of cosmic history. The geometry of space determines the center paradox's resolution. In infinite, flat space, there is no center and no edge. Every point is equivalent. Every location sees the same cosmic expansion. And our observable universe is an infinitesimal patch of an infinite whole. If the universe is expanding, what is it expanding into? This is the most common question people ask about cosmic expansion, and it's entirely natural. The question feels so obvious, so necessary, that not asking it would seem like a failure of curiosity. But here's the uncomfortable truth. The question itself contains a flawed assumption. The universe isn't expanding into anything. There is no surrounding void, no pre-existing space, no cosmic warehouse waiting to be filled. The answer is nothing, and that nothing isn't just an absence we haven't discovered yet. It's a fundamental feature of how expansion actually works. Our brains evolved to understand objects expanding into surrounding space. When you blow up a balloon, it expands into the air around it. When a city grows, it expands into the surrounding countryside. When a bomb explodes, debris expands into the space that existed before the detonation. every single example of expansion we encounter in daily life involves something growing into something else. An object expands. Space receives it. This pattern is so universal in our experience that we naturally assume it must apply to cosmic expansion as well. The universe is expanding, so it must be expanding into some larger arena that contains it. But the universe isn't an object in space. The universe is space. Space itself is what's growing. This distinction is subtle but absolutely critical. When space expands, it doesn't push into a surrounding void because there is no surrounding void. Space is all that exists. There is no outside because the concept of outside only makes sense when you have a boundary, and space has no boundary. Asking what the universe expands into is like asking what's north of the North Pole. The question seems reasonable until you realize it assumes concepts that don't apply. North is a direction defined by Earth's geometry. At the North Pole, every direction is south. There is no north of the North Pole because north ceases to have meaning there. Similarly, outside is a concept that requires a boundary between inside and outside. The universe has no such boundary, so outside is meaningless. Consider a cartographer working on a map. She decides to change the scale. Previously, 1 inch on the map represented 5 miles of actual distance. Now she changes it so 1 inch represents 10 miles. The map shows a larger area, but it didn't expand into anything. The representation itself changed. The relationship between the map and what it represents changed. Nothing physical grew. No surrounding space was consumed. The change happened within the internal structure of the map itself. Cosmic expansion works similarly. The distances between objects change. The scale of space changes. But this change doesn't require any external space to expand into. The change is intrinsic to space itself. General relativity revolutionized our understanding of space by revealing that it isn't an empty stage where events occur. Space is a dynamic, physical entity with its own properties. It can stretch, compress, curve, ripple, even propagate waves. The fabric of space, though we call it empty, is actually something, a geometric structure described by mathematical objects called metrics. The metric tells you how to measure distances between points in space. It specifies how much space exists between any 2 locations. And, crucially, this metric can change over time. Cosmologists describe cosmic expansion using a scale factor, usually written as A of t, where t represents time. This scale factor multiplies all distances in the universe. At some arbitrary reference time, we set it equal to 1. As the universe expands, A grows larger. When A equals 2, all distances have doubled. Galaxies that were 1 million light-years apart are now 2 million light-years apart. The scale factor captures the essence of cosmic expansion in a single number that changes with time. Currently, the scale factor is increasing, meaning distances are growing. The rate of increase is described by the Hubble constant. The Hubble constant, currently measured at about 70 kilometers per second per megaparsec, quantifies how fast space expands. A megaparsec is about 3.26 million light-years. The Hubble constant tells us that for every megaparsec of distance, recession velocity increases by 70 kilometers per second. This means space grows by roughly 7% per billion years. That doesn't sound like much, and locally it isn't. But this small rate, applied consistently across cosmic distances, produces dramatic effects over time. Right now, the space between Earth and the Sun is trying to expand. The distance is about 150 million kilometers, or 1 astronomical unit. Cosmic expansion attempts to stretch this distance by approximately 3 centimeters per year. 3 centimeters sounds tiny, and it is. But notice that the expansion is happening. Space itself is growing even at solar system scales. We don't notice this expansion because gravity overwhelmingly dominates. The Sun's gravitational pull on Earth is vastly stronger than the expansion of space between them. Gravity keeps Earth in a stable orbit despite the underlying expansion of space. The expansion is there, actively occurring, but completely irrelevant compared to the forces that actually control Earth's motion. This raises an immediate and troubling question. If space itself is expanding everywhere, why aren't we expanding too? Why doesn't cosmic expansion stretch atoms, molecules, humans, planets, solar systems? If space grows, shouldn't everything embedded in space grow with it? The answer lies in understanding the hierarchy of forces operating at different scales. Electromagnetic forces hold atoms together. These forces are governed by quantum mechanics and are extraordinarily strong at atomic scales. The electromagnetic force binding electrons to atomic nuclei is trillions upon trillions of times stronger than the expansion rate of space. Quantify this difference. The electromagnetic force holding a single hydrogen atom together exerts an influence that, at atomic scales, exceeds the expansion of space by a factor of about 10 to the 40th. That's 1 followed by 40 zeros. Cosmic expansion is utterly negligible compared to electromagnetic binding. Atoms don't expand because the forces holding them together completely dominate over the gentle stretching of space. The same principle applies at larger scales. Molecular bonds, chemical forces, the structural integrity of materials, all of these are governed by electromagnetic interactions that vastly overpower cosmic expansion. Gravity works similarly. The gravitational binding energy of solar systems, galaxies, and galaxy clusters exceeds the expansion of space within those structures. Earth orbits the Sun in a stable ellipse because gravity dictates its motion. The expansion of space between Earth and the Sun is irrelevant. Even at galactic scales, gravity wins. The Milky Way is not expanding. Our galaxy is held together by the gravitational attraction of its constituent stars and dark matter. The Andromeda Galaxy is actually moving toward us, not away, because local gravitational attraction between the galaxies overcomes cosmic expansion. Even our local group of galaxies, including the Milky Way, Andromeda, Triangulum, and dozens of smaller galaxies, is gravitationally bound. Cosmic expansion doesn't affect this bound system. The crossover distance where expansion begins to dominate occurs at scales of many millions of light years. Only at the distances between galaxy clusters does expansion overcome gravitational binding. Galaxy clusters are the largest gravitationally bound structures in the universe. The space between different galaxy clusters is expanding, carrying them apart. These vast voids between clusters are stretching, growing larger over time. This is where cosmic expansion becomes the dominant effect, where gravity can no longer hold structures together, where the stretching of space determines cosmic evolution. One of the most profound effects of expanding space manifests in the stretching of light itself. When light travels through expanding space, its wavelength stretches along with the space it traverses. This is cosmological redshift, the stretching of electromagnetic radiation caused by cosmic expansion. A photon emitted by a distant galaxy begins its journey with a specific wavelength. As it travels toward us through expanding space, the expansion continuously stretches the photon's wavelength. shifting it toward the red end of the spectrum. By the time the photon reaches Earth, its wavelength has been stretched significantly, sometimes by enormous factors. Cosmological redshift is fundamentally different from Doppler shift. Doppler shift occurs when a source moves through space. An ambulance siren shifts to higher frequency as it approaches you and lower frequency as it recedes, because the sound waves get compressed or stretched by the ambulance's motion through air. Light from a rocket ship moving away from you would be Doppler shifted to longer wavelengths, because the high-ice ship is moving through space. But cosmological redshift isn't caused by galaxies moving through space. It's caused by the expansion of space itself during the light's journey. The galaxy might not be moving through space at all. Space is simply expanding between us and the galaxy, stretching the light's wavelength in the process. The most distant observable galaxies show extreme redshifts. Light from galaxies near the cosmic horizon has been stretched by a factor of about 10. This means wavelengths have grown 10 times longer during the light's journey. Ultraviolet light emitted at 300 nanometers arrives as infrared light at 3000 nanometers. The entire electromagnetic spectrum shifts dramatically. Visible light becomes infrared. Ultraviolet becomes visible. X-rays become ultraviolet. This stretching allows us to observe the universe's early history. Young galaxies emitted most of their light in the ultraviolet spectrum. Expansion shifted that light to visible and infrared wavelengths, making it observable with optical and infrared telescopes like James Webb. Astronomers use redshift as a proxy for distance. The variable Zod represents redshift, defined as the fractional change in wavelength. A redshift of Z equals 1 means the wavelength has doubled. A redshift of Z equals 9 means the wavelength has increased by a factor of 10. There's a relationship between redshift and distance, though it's not perfectly linear because the expansion rate has changed over cosmic history. A redshift of 1 corresponds to a distance of about 7.7 billion light-years. A redshift of 10 corresponds to seeing the universe when it was only 500 million years old, with the light having traveled for over 13 billion years to reach us. Cosmological redshift has another consequence. As wavelength increases, photon energy decreases. The energy of a photon is inversely proportional to its wavelength. When a photon's wavelength doubles, its energy drops by half. This means the universe is literally diluting the energy of ancient light. Photons from distant galaxies arrive at Earth with far less energy than they had when emitted. This energy didn't go anywhere in the usual sense. It wasn't transferred to another object. It was simply diluted by the expansion of space itself. The total energy of all photons in a given region of space decreases over time as the universe expands. One of the subtle ways that cosmic expansion affects energy conservation in general relativity. The pattern of recession velocities caused purely by cosmic expansion is called the Hubble flow. Every galaxy participates in this flow, moving away from every other galaxy due to the expansion of space between them. The velocity calculation is simple. Velocity equals the Hubble constant times distance. Double the distance and you double the recession velocity. This linear relationship produces a strange consequence. At some distance, the recession velocity equals the speed of light. For the current value of the Hubble constant, this occurs at about 14 billion light-years. Galaxies at this distance are receding at exactly the speed of light. Galaxies farther than 14 billion light-years are receding faster than light. This seems to violate special relativity, which states that nothing can move through space faster than light. But there's no violation because galaxies aren't moving through space faster than light. Space itself is expanding, carrying the galaxies with it. Relativity limits motion through space but places no limit on the expansion of space itself. Space can expand at any rate. There's no cosmic speed limit on expansion. This distinction is crucial. If you were near one of these distant galaxies and measured its motion through local space, you'd find it moving slower than light. The faster-than-light recession is caused entirely by the cumulative expansion of space between us and that galaxy. The implications are profound. There are galaxies that exist, have always existed, that we will never see. Space between us and them has been expanding faster than light throughout cosmic history. Light, leaving those galaxies and traveling toward us, makes progress through local space but falls farther and farther behind as the space between us expands. The light is fighting a losing battle against cosmic expansion. These galaxies are real, physical objects containing billions of stars, but they are forever beyond our observational reach. They exist in regions causally disconnected from us, regions we can never access, measure, or know anything about except through theoretical inference. Where does new space come from? If space is expanding, creating more volume, more distance between objects, where is this additional space coming from? Is it being manufactured from nothing? Is there a reservoir of space somewhere being tapped? The question demands an answer, because creation ex nihilo, creation from nothing, violates our deepest intuitions about conservation laws. Yet, quantum field theory provides a perspective that makes this less mysterious. In quantum field theory, space is not truly empty. It's filled with quantum fields, invisible structures that permeate all of existence. Every point in space contains an electromagnetic field, an electron field, a quark field, fields for every type of particle and force in nature. These fields exist everywhere, even in regions containing no particles. Empty space, what we call vacuum, is actually seething with quantum activity. Virtual particles constantly pop into existence and annihilate in timescales so brief we cannot directly observe them. This quantum foam is not just theoretical. It has measurable effects like the Casimir force, where two metal plates placed very close together in a vacuum experience an attractive force caused by quantum fluctuations. Even with no particles present, quantum fields possess baseline energy called zero-point energy or vacuum energy. This energy is inherent to the fields themselves, a consequence of quantum mechanics. The uncertainty principle demands that fields cannot be perfectly still, perfectly at zero energy. There must be fluctuations, oscillations, activity. This vacuum energy fills all of space. It's not concentrated in one location or another. It's a property of space itself, uniformly distributed throughout the universe. Here's where it connects to cosmic expansion. The cosmological constant, the term Einstein added to his equations and later called his greatest blunder, might represent this vacuum energy. If empty space has energy, that energy has gravitational effects. But unlike normal matter, which creates attractive gravity, vacuum energy with negative pressure creates repulsive gravity. It pushes space apart rather than pulling it together. This repulsive effect drives cosmic expansion. As space expands, creating more volume, more vacuum energy appears because vacuum energy is a property of space itself. More space means more vacuum energy, which drives more expansion, creating more space in a continuous process. But quantum field theory creates a catastrophic problem. When physicists calculate how much vacuum energy should exist based on quantum mechanics, they get an answer that's 10 to the 120th power larger than what we observe. That's one followed by 120 zeros, the worst prediction in the history of physics. If vacuum energy were actually that large, the universe would be expanding so rapidly that galaxies, stars, atoms, even subatomic particles would be torn apart by the expansion of space. The fact that we exist at all proves vacuum energy is much smaller than quantum theory predicts. Why? Nobody knows. This is the cosmological constant problem, one of the deepest mysteries in physics. Einstein introduced the cosmological constant in 1917, not to explain expansion, but to prevent it. At the time, everyone believed the universe was static and eternal. But Einstein's equations predicted the universe should either be expanding or contracting. There was no static solution. To make his equations compatible with a static universe, Einstein added a term representing the energy of empty space itself, a constant value of energy density filling all of space. With the right value for this constant, the repulsive effect of vacuum energy could exactly balance gravitational attraction, allowing a static universe. Then Hubble discovered cosmic expansion, proving the universe wasn't static after all. Einstein called the cosmological constant his greatest blunder. He'd modified his beautiful equations to match incorrect observations. But the story didn't end there. In 1998, astronomers discovered that cosmic expansion is accelerating. Something is pushing space apart with increasing strength. The simplest explanation is Einstein's cosmological constant. Vacuum energy, the energy of empty space, drives acceleration. Einstein's blunder turned out to be one of his greatest insights. Empty space has energy, and that energy shapes cosmic evolution. But the value of the cosmological constant presents a fine-tuning problem. It must be positive to drive acceleration, but incredibly tiny or expansion would be far more rapid. The observed value sits in a narrow range that allows galaxies and stars to form, providing billions of years of relatively gentle expansion during which complex structures can develop. Why does the cosmological constant have this particular value and not some other value that would make the universe hostile to structure formation and life? One proposed solution invokes the anthropic principle and the multiverse. If an infinite number of universe regions exist with different values of the cosmological constant, we necessarily observe a value compatible with our existence. In regions where the constant is too large, expansion is so rapid that galaxies never form. In regions where it's negative, the universe collapses before stars can evolve. We find ourselves in a region with the right value simply because we couldn't exist anywhere else. This explanation troubles many physicists because it abandons the hope of calculating the cosmological constant from first principles. It makes our cosmic parameters seem like environmental accidents rather than fundamental predictions. Alternative theories propose that dark energy isn't a cosmological constant, but something dynamic called quintessence, a field that changes over time, or modifications to gravity itself at cosmic scales, or entirely new physics we haven't yet discovered. But all current observations are consistent with a simple cosmological constant. Empty space has energy density of about 6 times 10 to the negative 10th joules per cubic meter. This energy drives cosmic acceleration and will determine the universe's ultimate fate. We don't understand why empty space has these properties. We don't understand why the value is so small compared to quantum predictions. We don't understand whether it's truly constant or changing slowly over cosmic time. These mysteries sit at the foundation of cosmology, determining everything about cosmic expansion, yet remaining profoundly unexplained. Space itself is expanding, creating more space, more vacuum energy, driving ever faster expansion, and we're only beginning to understand how this impossible process actually works. In 1998, two independent teams of astronomers were studying distant supernovae, expecting to measure how much cosmic expansion was slowing down. For decades, cosmologists assumed that gravity would act as cosmic brakes. All the matter in the universe should be pulling on all other matter, gradually slowing the expansion that began with the Big Bang. The only question was how much deceleration. Would expansion slow enough that the universe eventually stopped growing and began contracting, or would it continue expanding forever but at an ever-decreasing rate? Both teams, the Supernova Cosmology Project led by Saul Perlmutter and the High Z Supernova Search Team led by Brian Schmidt and Adam Rees, set out to answer this question by observing Type Ia supernovae at vast distances. The results shocked everyone. Expansion wasn't slowing down at all, it was speeding up. The universe was accelerating. Distant supernovae appeared fainter than expected, which meant they were farther away than deceleration models predicted. Space had grown more during the light's journey than standard expansion could account for. Something was pushing space apart with increasing strength, driving acceleration that overcame gravity's attractive pull. This discovery was so unexpected, so contrary to theoretical expectations, that both teams spent months checking for errors, looking for any mistake in their observations or analysis. The acceleration was real. The 1998 discovery revolutionized cosmology and earned the Nobel Prize in Physics in 2011 for Perlmutter, Schmidt, and Rees. They had found evidence for dark energy, a mysterious component that fills space and causes repulsive gravity. Today, we know that dark energy makes up roughly 68% of the universe's total energy content. It outweighs all ordinary matter by more than 13 to 1. It even exceeds dark matter, which comprises about 27%. The remaining 5% is ordinary matter, everything we can see and touch, all the stars and planets and galaxies. Dark energy dominates cosmic evolution, determining the universe's ultimate fate. Our intuition says this should be impossible. Matter pulls on matter through gravity. The universe contains enormous amounts of matter distributed throughout space. All this matter should act as cosmic brakes, slowing expansion through mutual gravitational attraction. Every galaxy pulls on every other galaxy. This attractive force should fight against expansion, gradually draining energy from cosmic motion until expansion slows to a crawl or even reverses. Instead, we observe the opposite. Expansion is accelerating, growing faster with time. Something is overpowering gravity on cosmic scales, pushing space apart with ever-increasing vigor. The simplest explanation for dark energy is Einstein's cosmological constant, representing vacuum energy, the energy of empty space itself. In quantum field theory, empty space isn't truly empty. It's filled with quantum fields that possess baseline energy even in their lowest state. This vacuum energy has a peculiar property. While normal matter creates attractive gravity, vacuum energy with negative pressure creates repulsive gravity. It pushes space apart rather than pulling it together. This repulsive effect can drive cosmic acceleration, Here's the critical difference between matter and dark energy. As the universe expands, matter becomes more dilute. Spread a fixed amount of matter across twice as much volume, and you get half the density. Matter's gravitational influence weakens as space grows, but dark energy maintains constant density as space expands. More space means more vacuum energy, because vacuum energy is a property of space itself. If every cubic meter of space contains a fixed amount of dark energy, then doubling the volume doubles the total amount of dark energy. This creates a fundamental asymmetry. Matter's influence decreases over time, while dark energy's influence increases. Eventually, dark energy becomes dominant. The crossover occurred about 5 billion years ago. For the first 9 billion years of cosmic history, matter dominated. The universe was denser. Galaxies were closer together, and matter's gravitational pull dominated cosmic evolution. Expansion was slowing during this era, decelerating as gravity pulled on matter. But as expansion continued, matter spread thinner while dark energy maintained constant density. Around 5 billion years ago, dark energy became the dominant component. At that moment, expansion stopped slowing and began accelerating. We live in the age of acceleration, an era when dark energy controls cosmic destiny. This acceleration has profound consequences for the future. It creates a cosmic event horizon, a boundary beyond which light will never reach us no matter how long we wait. Currently, this event horizon sits at about 16 billion light-years from Earth. Galaxies beyond this distance are receding so rapidly due to accelerating expansion that light leaving them now will never reach us. Even traveling at maximum speed, the light makes progress through local space, but the distance between us and the light keeps growing because space expands faster than light can traverse it. These galaxies are permanently beyond our reach, cut off by an unbridgeable gulf of expanding space. While our particle horizon, the boundary of what we have already seen, continues growing as light from more distant regions reaches us, our event horizon is actually shrinking. Accelerating expansion means that galaxies currently within our observable universe are crossing our event horizon and disappearing from view. Not suddenly vanishing, but gradually fading as their light becomes increasingly redshifted, stretched to longer and longer wavelengths, dimmer and dimmer, until it becomes undetectable. Over trillions of years, galaxy after galaxy will cross the event horizon and fade into observational oblivion. The timeline for this cosmic disappearance is staggering. Currently, we can observe about 2 trillion galaxies throughout the observable universe. In roughly 150 billion years, assuming dark energy remains constant, only our local group of galaxies will remain visible. The Milky Way, Andromeda, Triangulum, and several dozen dwarf galaxies will have merged into a single giant elliptical galaxy. But beyond this merged structure, the sky will be empty. Every other galaxy, 97% of everything we can currently observe, will have been carried beyond the event horizon by accelerating expansion. Future astronomers will look out at the cosmos and see almost nothing, a single galaxy surrounded by vast darkness stretching to infinity. Could expansion eventually become so violent that it tears everything apart? This scenario, called the Big Rip, occurs if dark energy strengthens over time rather than remaining constant. In this model, dark energy isn't a cosmological constant, but something called phantom energy, with an equation of state parameter W less than -1. The equation of state describes the relationship between dark energy's pressure and density. For a cosmological constant, W equals exactly -1. For phantom energy, W is more negative than -1, creating even stronger repulsive effects that grow more powerful over time. If phantom energy exists, the destruction timeline is terrifying. First, galaxy clusters dissolve as expansion overcomes the gravitational binding holding them together. This occurs perhaps 20 billion years from now, as dark energy's repulsive effect grows strong enough to overwhelm the gravity-binding clusters. Next, individual galaxies are torn apart. The Milky Way would fragment, its stars scattered as space expands faster than galactic gravity can hold them. This might occur 50 billion years from now. Solar systems dissolve next. Earth would be ripped away from the Sun, planets scattered into interstellar space as expansion overcomes stellar gravity. This could happen months before the final end. Eventually, expansion becomes so extreme that it overcomes molecular bonds, then atomic bonds, then nuclear forces. Everything disintegrates. Atoms are torn apart into constituent particles. Even atomic nuclei fragment. The universe ends in a spasm of accelerating expansion that shreds reality itself down to fundamental particles. This is the Big Rip, cosmic doomsday through runaway acceleration. However, current observations suggest we're probably not headed for a Big Rip. Measurements of dark energy's equation of state give W approximately equal to -1, consistent with a cosmological constant within measurement uncertainties. While uncertainties allow W to be slightly different from -1, the data don't favor values more negative than -1 that would lead to phantom energy. The most likely scenario based on current evidence is that dark energy is truly constant, neither strengthening nor weakening over time. This leads to eternal exponential expansion, which is dramatic enough without tearing apart atoms. The most probable fate is heat death, the universe approaching a state of maximum entropy and minimum temperature. As exponential expansion continues forever, space grows without limit. Matter spreads thinner and thinner. The universe becomes colder and emptier with each passing eon. Star formation will cease in about 100 billion years when gas becomes too diffuse to collapse under gravity. No new stars will ignite. The existing stars will continue burning for a while longer, but eventually all stars exhaust their fuel and die. Red dwarfs, the longest-lived stars, can burn for trillions of years, but even they have finite lifespans. After several trillion years, the last stars will fade. The stelliferous era, the age of stars, will end. The universe enters the degenerate era, dominated by dead stellar remnants. These remnants, white dwarfs, neutron stars, and black holes, don't last forever. White dwarfs and neutron stars gradually cool, radiating away their remaining heat over unimaginable timescales. Black holes evaporate through Hawking radiation, a quantum process that causes them to slowly lose mass by emitting particles. Small black holes evaporate relatively quickly. Stellar mass black holes with masses of a few suns take about 10 to the 64 years to evaporate completely. Supermassive black holes take vastly longer. A black hole with 1 billion solar masses requires about 10 to the 100 years to evaporate. Eventually, even the largest black holes dissolve into radiation. After black holes evaporate, the universe approaches its final state. Temperature approaches absolute zero. Space contains nothing but isolated fundamental particles, electrons, positrons, photons, neutrinos, separated by distances that grow exponentially over time. Each particle is alone in an ever-expanding void. The the universe has reached maximum entropy, a state where no energy can be extracted, no work can be done, no interesting processes can occur. This is heat death, the thermal equilibrium of a universe that has expanded itself into insignificance. This fate takes incomprehensibly long to reach. Current age of the universe, 13.8 billion years, is nothing compared to the timescales involved. But if dark energy remains constant, heat death is inevitable. The universe will expand forever, becoming colder, emptier, darker, until nothing remains but isolated particles in infinite cold space. Return now to the paradox that started this journey. The center of expansion is everywhere because expansion has no center. This statement seemed contradictory, almost meaningless when we began. But now we understand what it actually means. Space itself expands. Galaxies don't move through space in the conventional sense. Space between them grows, carrying them apart. This expansion looks identical from every location because space expands uniformly everywhere. No point is special. No location serves as the center. Every observer sees the same pattern of recession, galaxies moving away in all directions, with more distant galaxies receding faster. The cosmological principle tells us the universe has the same properties everywhere and looks the same in every direction. Measurements confirm this to extraordinary precision. The cosmic microwave background is uniform to 1 part in 100,000. Galaxy surveys show the same large-scale structure in every direction. Tests of physical laws find them operating identically across cosmic distances. The universe exhibits no preferred location, no preferred direction, no center, no edge. Every point is equivalent. Every direction is equivalent. This perfect democracy of space means that asking what cosmic expansion is centered on is like asking what's north of the North Pole. The question assumes a framework that doesn't apply. Centers only exist relative to boundaries or external reference frames. A circle has a center because it has a boundary, an edge that defines which points are inside and which are outside. The center is equidistant from all boundary points, but the universe has no boundary. In flat, infinite space, there's no edge, no place where space stops. Without a boundary, the concept of center becomes meaningless. Centers also require external reference frames. The center of a circle can be defined relative to a plane containing the circle. But the universe has no external reference frame. Space is all that exists. There's no higher dimensional space containing our universe that would allow us to define a center externally. The balloon analogy we used earlier has limitations. A two-dimensional surface on a three-dimensional balloon appears to have no center on the surface itself. Creatures living on the surface see all other points moving away as the balloon inflates, with no point appearing special. But the balloon does have a center in three-dimensional space, a point in the interior equidistant from all surface points. This center exists in a dimension the surface dwellers can't access. Does our universe similarly have a center in some higher dimensional space we can't perceive? Current physics says no. General relativity describes space-time as a four-dimensional entity, 3 space dimensions plus 1 time dimension, and this four-dimensional structure is all that exists. There is no evidence for additional dimensions in which our universe is embedded, no external space containing cosmic expansion. The philosophical implications are profound. The Copernican principle is vindicated completely. We're not at a special location because all locations are equivalent. We're not at a special time because every era sees expansion, though different eras see different expansion rates. In some sense, we are at the center of our own observable universe. The cosmic horizon is centered on us. The last scattering surface is a sphere around us, but this doesn't make us special because every observer has their own horizon centered on them. Your observable universe and an alien's observable universe are different regions, overlapping but not identical. Neither of you occupies the center because there is no universal center, only observer-dependent horizons. We face epistemological limits that can never be overcome. No matter how advanced our technology becomes, we can never observe beyond our cosmic horizon. Most of reality, possibly infinite reality, is forever beyond our observational reach. If the universe is infinite, our observable region is literally 0% of the total. Everything we can see, measure, or know about is an infinitesimal fraction of what exists. This is humbling, but also liberating. The universe doesn't exist for our benefit. It doesn't care about our observations. It extends infinitely in all directions, following physical laws, creating structure, evolving according to equations that don't require observers. Yet mysteries remain. Why is the universe flat? The cosmological principle and observations tell us space has no curvature, but inflation explains this by stretching away any original curvature. Why is dark energy so incredibly small? Quantum field theory predicts vacuum energy 10 to the 120 times larger than observed. Why do we exist during this particular cosmic epoch? When stars shine, galaxies are visible, and the cosmic microwave background can be detected. In the distant past, before stars formed, there was nothing to observe. In the far future, after galaxies disappear and the cosmic microwave background fades, evidence of cosmic history will be lost. We happen to live during a window when the universe reveals itself. One possible answer invokes the multiverse and anthropic selection. If infinite regions of space exist with different properties, different values of fundamental constants, different amounts of dark energy, we necessarily find ourselves in a region compatible with our existence. Regions where dark energy is too large never form galaxies or stars. Regions where its negative collapse before life can evolve. We observe the values we do because we can only exist in regions with these particular values. This anthropic reasoning troubles many physicists because it abandons predictive power. Instead of calculating why constants have their values from first principles, we simply observe that they must be compatible with observers. The ultimate answer to what the universe expands into is that the question itself is wrong. The universe doesn't expand into anything because expansion doesn't work that way. Space itself grows. Distances increase. The scale factor multiplies all lengths. But this process requires no external arena, no surrounding void, no pre-existing space. The mathematical description of cosmic expansion, embodied in the Friedmann equations derived from general relativity, requires no special location. The equations treat every point identically. Solutions describe uniform expansion everywhere simultaneously. No center appears in the mathematics because none exists in reality. Observational confirmation is overwhelming. Every test designed to detect a preferred location or direction has failed. The cosmic microwave background is uniform. Galaxy surveys show the same structure in every direction. Supernovae measurements find the same expansion rate regardless of where we look. Tests of the cosmological principle performed with increasingly sophisticated instruments over decades, consistently confirm that the universe has no special location. We live in a cosmos where every point is the center of its own observable region, where space itself grows according to mathematical laws that treat all locations equally, where our cosmic address is completely unremarkable yet infinitely precious as the only region we can observe, study, and call home. As we've learned more about the universe, we've discovered how much more we don't understand. The historical progression shows expanding knowledge accompanied by expanding ignorance. We moved from Earth-centered cosmology to Sun-centered, learning we're not the center of the solar system. We discovered our Sun is one of billions in the Milky Way, learning we're not the center of the galaxy. We found the Milky Way is one of trillions of galaxies, learning we're not the center of anything. We measured cosmic expansion and found it's the same everywhere, confirming there is no center. Each step revealed greater cosmic democracy, places us in an increasingly unremarkable position, yet each step also revealed deeper mysteries. What is dark matter? What is dark energy? How did structure form? Are we alone? What lies beyond our horizon? Increasingly sophisticated instruments will refine our measurements. The James Webb Space Telescope observes the earliest galaxies with unprecedented clarity. The Nancy Grace Roman Space Telescope will map cosmic structure across vast volumes. Future extremely large ground-based telescopes with mirrors 30 to 40 meters across will resolve details invisible to current instruments. Each new instrument pushes observational limits further, reveals fainter objects, measures cosmic parameters more precisely. Yet, each improvement also shows us how much remains unknown, how many questions we haven't answered, how vast the territory of ignorance remains compared to the small island of knowledge. The center of the universe is everywhere and nowhere. This truth defies human intuition evolved in a world where expansion always requires something to expand into, where centers and edges define objects, where space seems like an empty stage. But reality operates according to deeper principles. Space is dynamic, expanding everywhere equally. The universe has no center because it needs none. Expansion occurs uniformly throughout infinite space. Every point sees the same pattern. Every observer is at the center of their own observable cosmos while simultaneously being cosmically unremarkable. This perfect encapsulation of our place in reality, simultaneously central and insignificant, at the heart of observation yet lost in infinite space, captures the profound strangeness of existence in an expanding universe. We are the universe observing itself, asking questions about its own nature, discovering that the center we sought was never a place but a perspective, never a location but a feature of observation itself. And in that realization, we find not diminishment, but wonder at the magnificent structure of reality.